In talking about the interior of the Earth, it has a very long and relatively complex history. First of all, the Earth was formed about 4.5 billion years ago here in what was then just a great big nebula. The nebula was a large concentration of gases and other elements. Those gases and elements started to collect into particular bodies. The most dense part was the very center, which became our sun, and there were a handful of very large masses that formed from those gases and elements. Those became the planets of our solar system. When the Earth was first formed, all those elements and materials that first came together created a very, very hot, molten ball, really. It was just Earth had nothing but a molten surface. And it was constantly being bombarded with asteroids and other material from inside of the nebula. It was a very violent time on the Earth. Over time, the surface of the Earth cooled, and as it cooled, the materials crystallized and formed lots of igneous rocks, which, of course, as we saw in chapter 17, those igneous rocks would break down into sediments or metamorphosize, forming the sedimentary and metamorphic rocks. Now, the Earth was so hot, it induced a lot of radioactive decay from many of the heavier elements down in the center of the Earth. That heat kept propagating up to the surface, so as the heat from the radioactive decay moved towards the surface, it would melt the interior of the Earth. So the outside cooled, but the inside stayed hot because of this radioactive decay. This melting occurs in pockets. These hot spots are in pockets on the inside of the Earth. It's not consistent throughout the entire interior of the Earth. Now we need to talk about something called differentiation, which is the melting and gravitational settling of the heavier elements, separates or differentiates the heavier elements from the lighter elements at the surface. And all of this gave the Earth its present structure of layers, with the heaviest elements at the core, with the lightest elements at the surface. Now, the very, very, very center of the Earth is the core. The outer portions of the core is still molten because of the intense pressure and the heat down there. And it's primarily made of iron, and actually is the source of the Earth's magnetic fields. The pressure at the center of the Earth is somewhere around 3.5 million times the pressure that we feel here at the surface. It is absolutely intense pressure that you would feel at the core of the Earth. The temperatures at the core reach somewhere on the range of 6,000 degrees Celsius. Now, how do we know all this? Well, all of this has been deduced from the following points. The Earth's magnetic field induces magnetic properties in rocks. We talked about that back in magnetism. Magnets were created from rocks, lava flows that were cooling during strong magnetic field periods. We can look at the igneous rocks that have formed over the many, many, many millennia of the Earth, of the Earth's history, and we can tell the strength of the magnetic field, which will in turn tell us a lot more about what's happening inside of the Earth. Another thing that we can determine a lot from is gravity effects. Gravity has been different over the period of life of the Earth. And so it helps us to understand a little bit more about the size of the Earth and how the Earth is reacting, so on. as well as current gravity effects. For instance, using the density of the crust and the size of the Earth is more massive than what that density and volume would say that the Earth should be. So that tells us that there are much more heavier elements closer to the center of the Earth, and the density at the surface is light comparatively. Another thing that tells us about the Earth's internal structure is heat flow. The direction that heat travels, if the Earth were cool at the center, then the heat would flow from the surface towards the center of the Earth. But that's not what happens. The heat is actually flowing from the center of the Earth towards the surface and then out to space. So that tells us a lot. Another thing that really tells us a lot more about the interior of the Earth are vibrations, waves, particularly seismic waves. Now, seismic waves is just a fancier term for earthquakes. Seismic activity is any wave that's propagating through the Earth. When it's large enough to have an effect on populations, it is known as an earthquake. Now, when you have a wave, an earthquake, it begins at some point and then radiates outward through the Earth. We've noticed things like earthquakes in large explosions, particularly in nuclear explosions. That's where we can definitely feel lots of earthquakes that way. And we'll come back to that in a second. Now, when we look at earthquakes and waves that propagate through the Earth, there are three basic types. The ones that go through the Earth are known as P waves and S waves. P wave, or pressure wave, is what we call a longitudinal wave. That means that when you look at the wave, it is a wave of compression. This compression moves back and forth. And so you have regions where it's compressed, regions where it's expanded, and just oscillates back and forth and back and forth. And that region of compression will propagate all the way down to the end of the spring. That is a longitudinal wave, also known as a P wave in earthquakes. This is the wave that does most of the destruction in an earthquake. S wave is also very damaging from an earthquake, but not the worst. P wave is definitely more. S wave stands for shear wave. This is what we call a transverse wave. That means that instead of a compression moving along the spring, a transverse wave is going to be that whatever is moving moves side to side, up or down, basically in any path perpendicular to the direction the wave is going. So the wave is moving forward, but the oscillation is up and down. Anytime that happens, that is a transverse or shear wave. Both of these types of waves propagate through the center of the Earth. However, if it reaches near the surface, you get this up and down wave. That is what you would see, say, waves at a beach. The ocean waves are the crests and the troughs, the surface waves, surface manifestation of waves that are happening underneath. These are the least powerful and the slowest of these three different types of waves. Now, the interior of the Earth is divided into three basic parts. The outermost part is the crust, a very thin outer shell. Beneath that is the molten part of the Earth called the mantle, much, much thicker, and the very center is the core. We're going to go through each of these three. The crust covers the entire Earth. There are two parts to the crust. You have the oceanic crust, which is this region here at the bottom of the ocean. Notice it is much thinner and made of more of a basaltic type of rock. Remember, the difference between a basalt and a granite is how quickly the magma has cooled. Since it's at the bottom of the ocean, it is much more dense and so a lot heavier, but it's also a lot thinner. Then you have the continental crust, which is made primarily of granite. It's much less dense than the basaltic base of the ocean. And it's much larger, so it comes up above sea level, of course, and these are where our continents would, or land masses would be. This layer right here, this boundary between the crust and the mantle, is what we call the Mohorovicic discontinuity. Just the layer between the mantle and the crust. We know that where that exists because there is a change in seismic activity when it reaches the Mohorovicic discontinuity. The mantle, the layer beneath the crust, is a very thick shell between the crust and the core. This takes up about 80% of the Earth's volume, is about 2/3 of the Earth's mass, and composed mainly of the rock that we call olivine, which is a ferromagnesian silicate. The way that we can tell about what's in the mantle is from seismologic data, nature of meteorites when they hit the Earth, and then materials also ejected by volcanoes. All of these will tell us more about what is in the mantle and about its mantle's behavior. Now, there is a close correlation to silicate chemical composition of stony meteorites. This is the basalt correlation. It's an interesting correlation between these meteorites and the most common volcanic types of rock. And so that tells us a lot about the history of the Earth, including that some of these meteorites that we deal with were also formed in the same way that the Earth was. So you have basically cousins to the Earth out in space that sometimes come down, and we've got evidences of what those things are made of, so on. Your book describes this in a lot better detail than I could in the short time I have. Now, if we look at the core of the Earth makes up 15% of the Earth's volume, so not a whole lot, more than what the crust of the Earth takes up, but far less than the mantle. And yet, inside of the core, you have 1/3 of the Earth's mass. Here's how we know where about the core. When we look at P wave seismologic activity, that those P waves will propagate through the Earth. Through the mantle, there's no problem, no deflection, a little bit of curving of these waves off to the side. But all of a sudden, there is a change when you go about 103 degrees around the Earth. When these waves hit the core, they are deflected, very much like a light wave is deflected through glass, and as a result, you end up getting a wave that is deflected towards the far side of the Earth. Now, that leaves a region here between 103 degrees and 142 degrees, either direction from the seismologic activity, where you will not pick up any P waves at all. And yet you do have waves that appear anywhere beyond 142 degrees either direction on the opposite side of the world. This will tell us not only how large the core is based on this 103 degree line, but also the deflection of these waves will tell us the density and the material of the core. What's the core made of? How dense is it? How hot is it? And so on. And so from that, we can determine the shape and the size of the core. But if you look at S waves, those are the shear waves, the side-to-side waves that we deal with in seismic activity. There's a much larger shadow. One important thing about S waves is that they do not propagate through solids as easily. They propagate through the liquid, all right, but they do not propagate through the solid. Let me come back to that for just a second. Let me refine that better. It propagates through the liquid mantle quite easily, but the outer layer of the core has a liquid part to it, and that causes the S waves to not propagate through the core. So we still have the same 103-degree line, but there is no propagation of S waves through the core, which means you have absolutely no S waves on the far side of the Earth. From this, we can tell that the core has two layers. The outer layer is liquid, and the inner layer is solid. And both of those points are supported by the behavior of S waves and P waves through the core of the Earth. There are other evidences of what the core of the Earth is like. Iron meteorites, again, similar to the meteorites we were talking about with the mantle. These meteorites are mostly iron or iron-nickel alloys in their cores, and they are thought to mimic the chemical composition of the core. Now, here's the other big evidence of the core. Remember how I said at the core of the Earth is the source of the Earth's magnetic field? Well, the magnetic field comes from the turbulent flow within the liquid portion or the outer layer of the core. Now, in order for a magnetic field to be emitted, that must indicate that the material in the core has to be able to conduct electricity. Since most of the Earth is made of iron, and iron conducts electricity, it's common sense that that is what the core of the Earth is made of. Now, both of these points, the meteorites and the magnetic field data, are consistent with the ideas of an iron core. All the puzzle pieces fit together, tell us that it's an iron core in the center of the Earth. Now, there are a couple of layers of the Earth that we skipped over briefly, but let's cover them here. The first layer that we deal with is the asthenosphere. It is in the upper region of the mantle, an extra hot elastic semi-liquid. That means it's partially liquid and partially solid. And that's this region here, close to the upper layer of the mantle. There's still a little bit of mantle up above it, but not a whole lot. The reason we know it's there is that there is a sharp decrease in seismic wave activity. And so there has to be a layer of liquid there to start that will deflect a lot of the seismic waves. The other layer that we want to talk about is the lithosphere. The lithosphere is the solid layer above the asthenosphere, which includes the crust and the uppermost part of the mantle. And this lithosphere is what is critical in talking about plate tectonics, because the lithosphere is made up of many rigid plates that float on top of the asthenosphere and the rest of the upper parts of the mantle.